Everyone, this is the LMPS circuit, linear mode power supply, using the Zener diode as the voltage regulator. And initially we are having the 230 volt AC supply, which is of the frequency of 50 Hz. And initially we are having a fuse for the protection. Later we'll see about this this component. And with the fuse, this is a transformer. And for firstly we are using the rectifier. We are using the bridge rectifier. So this is the anode and this is the cathode, and this is also similarly anode, cathode, and this is cathode, anode, and this is cathode and anode. Okay. And now what you are doing is, how we are connecting the rectifier is anode, cathode meeting one point, and here also anode meeting one point. The first diode, this diode is connected with the D3, and the second diode D2 is connected with the D4. Right, this is how we are connecting the bridge rectifier. And next here we have one capacitor, and to find the value of this capacitor we are having one formula. Okay, C is equal to I by 2 into frequency into the V ripple. Okay, so this is the circuit. Actually, for what we are designing is, in the output we have to get the 230 volt will be converted to 12 volt and also the 5 volt with the current rating of 100 milliamps. Okay, both also 100 milliamps. So this is how we are converting. And for to find this capacitor value, we are assuming the V ripple voltage as 1 volt. We can take from 0 to or 0.5 to 1 volt we can take. Okay, so we are assuming as 1 volt, and we already know we are designing for 2 current ratings, so we are having 200 milliamps. So 200 milliamps by 2 into the frequency is 50 and V ripple is 1. Okay, when we are solving this, we will get 2000 microfarad. Generally we will take the capacitor in the range of microfarad, so we are taking as 2000 microfarad. So the standard value we can take like this as 4700 microfarad. Okay, so this is what we are taking. And here this capacitance we can take like a 0.1 microfarad, just enough. This is just for the filtering value. Okay, so up to the capacitor we have seen. Next we will see about the regulators. 2 Zener diode regulators to get the 12 volt one as output and the 5 volt as the output. So initially we are having the resistors R1 and R2. Okay, so one more thing we will see that initially for this 12 volt is the V maximum we have seen, right? Vm is equal to 12 volt. Okay, so to convert this into RMS value, what we will do? To convert this RMS value, we will do Vrms equal to Vm into root 2. Okay, so 12 into root 2, approximately we will get 16.9 volt we will get. Okay, 16.9 volt we will get. And we have diode drop. So in this diode, the bridge rectifier, so this is the initial sine wave, right? So this is the initial sine wave we will get. And in the output, as this is a full wave rectifier, in each time this is the these are the output waveform, right? Actually we have to draw exactly. These are the output waveform we will get. So each time 2 diodes will conduct. Initially for the positive cycle D1 and D3 will conduct, and for negative cycle D2 and D4 will conduct. So likewise if we see, for each time 2 diodes are conducting. So the diode drop in each time will be what? For 1 time 0.7, for 2 times means 1.4 is the diode drop. So when we are subtracting the diode drop from this Vrms value, we will get approximately minus diode drop. Okay, diode drop, in the diode drop what we will get? We will get approximately 16 volt we will get. Okay, this is the 16 volt we are getting, and this voltage is the voltage across this. We can take across this or this. Okay, we are taking across this. it is a parallel, right? Both have the same circuit. So 16 volt we are taking here, and this is the 12 volt Zener diode VZ, and this is the 5 volt Zener diode we are taking. Okay, 5 volt Zener diode. Now we are having the two values, 16 volt and 12 volt. We can find the voltage across this. What we will get? We will get 4 volt. 16 minus 12, 4 volt we will get. Okay, and also what is our max total current here? 200 milliamps. It starts flowing from here. So when this 200 milliamps flows here, okay, we'll keep this. And also Zener minimum current starting will be 20 milliamps. And here also 20 milliamps. Okay, so if this from this part only the current is splitting. So if this is 20 and this is 20, what will be the current here? Across this will be 40 milliamps. So across this resistor the voltage is 5 and the current is going is 240 milliamps. Okay, 240 milliamps. And also here the voltage here the current, if this 200 is splitting into 100 and 100, here will be 100 milliamps generally from the total current, and this 20 milliamps here. So total current flowing will be 120 milliamps, and the voltage across this 12 minus 5, that is 7 volt. Okay, so this is what we are getting. And this is okay, everything okay. Then now we are going to calculate the value of R1 and R2. So how we will calculate the R1? Generally we know R1 is equal to V by I. Okay, R is equal to V by I, and here the voltage across first resistor is 4 volt, and the current across them is 240 milliamps. Okay, 240 milliamps. Similarly R2 is equal to V value is 7 by the current is 120 milliamps. What we'll find the value of this. So we'll get the value of 16.6 and 58.3, and if you calculate the power rating, the voltage into current, it will be 3.36 for R1 and 0.84 watts for R2. Okay, so now we have seen everything, and if we want the indication for output whether the supply is coming or not, we can keep here, we can have one resistor here, and we can have one diode, sorry not diode, it's a LED. Okay, we can have one LED, and we can check the output. Okay, and next what we are going to see is so initially we had fuse for protection, right? One more circuit is there, MOV. It is metal oxide varistor. Also we can call it as a voltage dependent resistor. What it will do actually is, when the high current like lightning or anything affects the circuit, it destroy itself and sort the path. It sorts the path and protects the remaining circuit. This is the work of it, and it is actually connected in parallel, and there must be a fuse in before it. One more component is there, we can call it as NTC. It is actually one more component is NTC. It is actually a negative temperature coefficient. So if temperature increases, this value of resistance will decreases. So if the temperature increases, if resistance decreases, the current will be high. Suppose if we have high temperature, when the surge occurs, that lightning surge or current surge occurs at a high temperature. So when temperature when the current occurs, when the high current will be there, that time the resistance will go high, and that I value will decrease and the resistance value will increase. So this is NTC. And why we are using NTC or negative temperature negative temperature, not PTC, because it is the inverse of it. When temperature increases, resistance decreases. This is the inverse relation, and it is usually connected in series with the circuit. So this is the LMPS circuit using the Zener diode as voltage regulator.